Physics requires a precise dialect to describe how things relate to one another. To explain change, we use the mathematical framework of calculus, which connects abstract concepts to concrete measurements like position, velocity, and acceleration. While biology finds order by naming and chemistry by composition, physics finds order through relationships. Calculus is the study of how position, velocity, and acceleration connect, as one quality describes how the other is changing. Consider the case of a speeding ticket. If a car's position is given by x equals t squared, and it passes a detector at t equals 20 seconds, standard algebra tells us where the car was, but not its instantaneous velocity at that exact moment. If we attempt to use an average velocity calculation over a 5-second interval, from 15s to 20s, we find an average velocity of 35 meters per second. This is too slow, because it's an average over time, not a snapshot. To find the instantaneous velocity, we use the concept of limits, shrinking the time interval. As the time gap approaches 0, the average velocity calculation gets closer and closer to the actual velocity of 40 meters per second. The derivative is the science of right now. It is an equation that describes the rate of change at an exact moment. Velocity is the derivative of position, and acceleration is the derivative of velocity. Decoding the notation, dx over dt means the derivative of position, x, with respect to time, t. Another common notation is f prime of t, where it is the derivative of the original function f of t. The power rule is a shortcut for solving derivatives. To apply it to t squared, you identify the exponent, move it to the front, and subtract 1 from the exponent, resulting in 2t to the power of 1. Applying the power rule to our speeding case, the position equation x equals t squared becomes the velocity equation v equals 2t. At t equals 20 seconds, the final velocity is 40 meters per second, confirming the speeding verdict. The power rule logic holds for complex variables, including coefficients, fractions, and negatives. It is applicable regardless of whether the exponent is a whole number, a decimal, or a negative. Physics often involves angles, projectiles, and orbits, requiring trigonometry. To understand these wave functions like sine and cosine, we need to apply derivatives to them. The slope of the sine wave changes across its curve. The slope is 0 at the peaks and troughs, positive as it rises, and negative as it falls. If we track the slope of the sine wave, we get the red wave. This red wave looks exactly like cosine, which is because the derivative of sine x is cosine x. The unchangeable constant, e to the power of x, is a unique function. It is the only function where the rate of change, or the derivative, is equal to the value of the function itself. Calculus allows us to go down the chain using derivatives, from position to velocity to acceleration. To go backward, finding position from acceleration, we use integrals, which is the next step.